Welcome guys. So here comes I think the difficult question in this exam is 61. Actually I didn't get the right answer when the first time I did it, because I think there's there's a seldom numbers theory in the GRE, but actually 61 is a numbers theory. What is the greatest integer that divides p to the fourth minus 1 for every prime number p greater than 5? Okay. So p to the fourth can be written as p squared minus 1 p plus 1 p to the square plus 1. And there's multiple ways to solve this problem. Okay, so let me first say that a divides p to the fourth minus 1. And the reason is since p is larger than 5, so p is odd. So p minus 1 is even, p plus 1 is even, p squared plus 1 is even. So this 3 factor contains 3 factor of 2. So the answer is, it must contain 8. So a divides p to the fourth minus 1, a. So this one is not okay. B is not okay. C could be okay. D could be okay. E could be okay. Okay. And the second one is, and the second statement I want to show is 3 divides p to the fourth minus 1. How do we prove this? Okay, so there are 2 ways to prove this. The first way is since every number divided by 3 have only 2 kind of remainder. One is 0, one is 1, one is 2. So p is either 1 mod 3 or p is either 2 mod 3. So p to the fourth is 1 mod 3, and the p to the fourth is 16 mod 3. But basically 16 mod 3 is 1 mod 3. So basically p to the fourth minus 1 is 0 mod 3. So 3 divides p to the fourth minus 1. Okay. So other method is called the Fermat little theorem. Actually I proved this theorem in English and the Mandarin version, and I will leave the link below. Basically, if a is coprime to p, then ap minus 1 basically is 1 mod p. So this tells you that p squared must be 1 mod 3. So you can prove that p to the fourth is 1 mod 3. So now we prove that a divides this, 3 divides this. Okay, so what is the last? What we need to know is 5, right? Whether 5 divides p to the fourth minus 1. Okay, and due to the Fermat little theorem, p to the fourth equals to 1 mod 5. So basically 5 divides p to the fourth minus 1. So we have 8 divides p to the fourth minus 1, 3 divides p to the fourth minus 1, 5 divides p to the fourth minus 1. So it looks like the answer should be 8 times 3 times 5. So it's 120. However, so this is the trap that which is difficult to see. So when I first solve this question, I choose D. But when I see the answer is E. So So I don't see how to get the final two vectors. How to get the final two vectors. Okay, so let us do more careful analysis. This p to the 4 minus 1 can be written as this. So p is not greater than 4. So there are two kind of prime numbers which is greater than 4. One is the 4k plus 1 type. One is the 4k plus 3 type. Okay. So for the first one type, if you plug p equals to 4k plus 1 into this, then you get 4k plus 2, 16k squared plus 8k plus 2. So you see there are 4, 2, and 2. So you see 16 divides p to the 4 minus 1. Okay, how about p equal to 4k plus 3? Okay, 4k plus 2, 4k plus 4, 16k times 24k plus 10. So you see there are 2, 4, and 2. So also 16 divides p to the 4 minus 1. So 16 divides p to the 4 minus 1, 3 divides p to the 4 minus 1, 5 divides p to the 4 minus 1. These two due to the Fermat little theorem. Maybe you can still use this to prove Fermat. You can use the Fermat as the little theorem to prove this. Because 5 of 16 is 16 minus 12. Let me see. Is it correct? No. So you cannot do this. So this 16 you need to figure out by yourself. So the answer is 16 times 3 times 5. 240. This is a difficult question. Actually, I got answer wrong in the first time because I chose D. Yeah, so the answer is E. The answer is E. Very difficult question. So, please do subscribe to my channel, and if you think what I did something right, I did something wrong, please leave a comment below, and I will go to check it. Thank you.